Hello, everyone, and thanks for watching. This talk is based on a joint work with Theo McKenzie, and it's going to be about constructions of high-girth near-Ramanujan graphs with lossy vertex expansion. So let's begin with some setup. So in this talk, we will use G to denote a graph, and this graph is going to have n vertices, and it's going to be a deregular graph. And with this graph G, we associate an adjacency matrix A, which has n eigenvalues, which in sorted decreasing order are lambda 1, lambda 2, down to lambda n. And lambda 1 is always equal to d by virtue of the all ones vector being the top eigenvector of a deregular graph. And we use lambda of g to denote um, the ball in which all eigenvalues except for the top one fit. So as you can see in this diagram, there's one eigenvalue at d, and the remaining eigenvalues are between negative lambda of g and lambda of g. And we use the term spectral expansion to refer to this quantity lambda of g. And more precisely, it is the minimum of the second largest eigenvalue and the negation of the smallest eigenvalue. More simply, it's the second largest absolute eigenvalue of a graph. Now, in a deregular graph, a theorem of Alon and Bopana uh, gives a lower bound on how small this number lambda of g can be. In particular, this theorem says that lambda of g is always at least 2 square root d minus 1 minus a small amount which goes to 0 with as n goes to infinity. And we will use the term Ramanujan graph to describe graphs G whose spectral expansion is less than or equal to 2 square root d minus 1. And similarly, by extension, we're going to call a graph near Ramanujan if lambda of g is at most 2 square root d minus 1 plus little of 1. Now, why should we care about spectral expansion? So the first thing is it actually implies various forms of combinatorial expansion. And in particular, it implies a good spectral expansion implies good edge expansion in the graph. Second, it actually controls the mixing times of random walks. So the smaller lambda of g is, the faster a random walk mixes. And finally, there actually exist efficient algorithms to compute lambda of g. So if we wanted to know whether a graph is a good edge expander, one way to do this would be to check whether it's a good spectral expander by just computing the second largest absolute eigenvalue. And if it's small, we know it's a good edge expander. So now to sort of see what a typical graph satisfies in terms of spectral expansion, as well as other forms of expansion that we will be interested in this talk, let G be a uniformly random deregular graph. Some properties include, number one, the graph has great spectral expansion. In particular, a random graph is near Ramanujan with high probability. That is, except for the trivial eigenvalue, at D, all other eigenvalues are almost in this Ramanujan interval. They almost meet the Alon-Bopana bound. Now, a second property is random graphs also have near perfect edge expansion, where the edge expansion for sets of size delta n is defined to be the set S such that the number of edges leaving the set is as small as possible. And as you can see, like the edge expansion of any set is bounded by at most d, whereas random graphs nearly achieve that bound. In particular, the edge expansion random graph for sets of size delta n is d minus 2 minus some quantity epsilon, which depends on delta. And finally, the third parameter of interest in this talk is vertex expansion. Namely, for sets of size delta n, if I choose a set and then look at all the vertices that are adjacent to a vertex in the set S, how large is this number of is a set of adjacent vertices? And once again, it's easy to see that a vertex expansion graph cannot exceed D, whereas in a random deregular graph, the vertex expansion actually gets pretty close to D. In particular, it's at least this number, D minus 2 minus some small constant epsilon, which depends on delta. And now here I've told you like 3 really good properties of random graphs. And the motivating question for us is whether all 3 of these properties are connected. So in the classic spectral graph theory literature, it's actually very well understood that if your graph is a good spectral expander, then via a simple application of the expander mixing lemma, we know that the graph is also a lossless edge expander. That is, it has near perfect edge expansion. And also, it's not hard to see that if you have lossless vertex expansion, thus your vertex expansion is very close to D, then that also implies that you have lossless edge expansion. But the main mystery for us is whether having good spectral expansion says anything about lossless vertex expansion. Okay, so first question you could ask is, even lossless notwithstanding, does spectral expansion imply anything at all about vertex expansion? And a partial non-trivial answer was given by Kahale, where he proved that if G is a near-Ramanujan graph, then actually for sets of size delta n, the vertex expansion is lower bounded by D over 2. But it falls short of lossless by a full factor of 2. And then question here is whether the statement that Kahale made is tight or not. And in the same paper, Kahale actually proved that the statement that we just saw is nearly tight. In fact, he shows that there's an infinite family of near-Ramanujan graphs such that for every graph in this family, the vertex expansion is bounded by D over 2. So in particular, this exhibits that knowing that a graph is near-Ramanujan alone does not imply that you have a lossless vertex expander. So at this point, it seems like this question has been settled. But let's zoom into Kahale's example to understand what these infinite family of near-Ramanujan graphs look like. And the reason for doing so is because random graphs are nevertheless good lossless vertex expanders. So the motivating question here is, do Kahale's graphs have properties that random graphs wouldn't have? Like what is the property of a random graph that actually distinguishes it from the graph that was given by Kahale? And here's actually what Kahale does in his construction. He starts with a very particular gadget. The gadget is a complete bipartite graph with 2 vertices on the left-hand side and D vertices on the right-hand side. So these 2 vertices have degree D, and these D vertices have degree 2. And now what you do is you take some near-Ramanujan graph, G prime, and somehow insert this gadget over here into this near-Ramanujan graph. So once Kahale plants this K2D gadget within a Ramanujan graph, the effect it has is the graph still stays near Ramanujan, but the set L here within this gadget actually has vertex expansion D over 2. As you can see, the set of 2 vertices L expands into D vertices. So now, what is it about this example that's different from a random graph? And it's the fact that actually this K2D structure has many short cycles within. So the probability of such a structure occurring within a random graph is really small. It's 1 over polynomial in n. Now, let's understand whether having many short cycles in a K2D is actually the real barrier for uh, whether this graph has poor vertex expansion. And if so, the next motivating statement that was also proved by Kahale was, it's actually a purely combinatorial statement. And it says if any graph has large girth, namely girth larger than c times log n, then the vertex expansion of certain small size sets, where I guess small here is roughly n to the c over 4, where c is this constant in the girth. So yeah, these sets are always a size at most n to the quarter or so. Those actually have near perfect vertex expansion. The vertex expansion of every such small set is 1 minus little of 1 times d. And a more simple way to say the same statement is very small sets within a high girth graph expand losslessly. So this motivates the question of study in our work. If you have a near-Ramanujan graph, and you also know that this near-Ramanujan graph you have in hand has high girth, where here high girth means at least some constant times log base d minus 1 n, then does that actually mean that your graph is a lossless vertex expander? In particular, is there a constant delta such that all sets of size delta n have lossless vertex expansion, at least like d minus little of 1? And that actually leads us to the main contribution of this work. And it's the following. There's actually an infinite family of graphs. Now, each graph in this infinite family is near Ramanujan, namely, it has spectral expansion at most 2 square d minus 1 plus little of 1. Each graph in this family also has high girth, at least c times some logarithm in n. But the vertex expansion of sets of size n to the some 1 minus some constant epsilon, namely there exist some sets of sublinear size whose expansion is at most d plus 1 divided by 2. So in particular, what we show is this adding this high girth assumption on top of near Ramanujanness doesn't actually guarantee that you have a lossless vertex expander. Like there exist graphs with poor vertex expansion. And in the remaining time, I'm going to try to give a sketch of how this proof works. And the starting point of this construction is actually a construction of Ramanujan graphs which have high girth. Namely, Lubotsky, Phillips, and Sarnak gave a construction of Ramanujan graphs which were d-regular, where d was a prime number plus 1. And in this infinite family of graphs that they gave, the girth was actually at least 4/3 times log n base d minus 1. And the second ingredient that we will need is a certain gadget graph. Namely, this gadget graph is a bipartite graph which has high girth. The girth is omega log n. Now, the left side actually has vertex expansion bounded by d minus 1 over 2, because it's a 2 comma d biregular graph. So just by virtue of it being a 2 comma d biregular graph, the left side has vertex expansion roughly d over 2. And actually, why can this second bipartite gadget be constructed? So you can construct such a graph by taking some high girth d-regular graph. So here I've drawn a graph, pretend it's high girth and d-regular. And what you do is you subdivide each edge. The old vertices are orange. Now I add new vertices where I take every edge and subdivided into two edges with a vertex in between. And now you can treat the orange vertices as the left vertex set and the blue vertices as the right vertex set. Now, the next part of the talk is going to be to show how one mixes ingredients 1 and 2 to actually come up with the graph construction that's promised by our theorem statement. So it's best illustrated by the sequence of pictures below. So start with the Lubotsky-Phillips-Sarnak-Ramanujan graph G, which is drawn here, and then choose any vertex V in this graph and look at a radius R ball around V. And now imagine R is less than the girth over 2. So actually, this ball is going to look like a tree. So now the graph looks like a ball, which connects to like some really large segment in the graph. Now the second step is actually to delete the ball from this LPS graph. So now once we've removed the ball, we've left a bunch of holes. Namely, there's a bunch of vertices in the remaining graph which have degree only d minus 1. And the next step we do is we take a copy of the graph H, where let me remind you what H was. H was this 2 comma d minus 1 biregular graph that was promised in ingredient number 2, which has high girth. And also the left side has vertex expansion at most d minus 1 over 2. And we take H. Now, within H, every vertex on the left-hand side has degree d minus 1. Every vertex on the right-hand side has degree 2. So we add a bunch of half edges, one half edge to every vertex on the left-hand side, d minus 2 half edges to every vertex on the right-hand side. So now every vertex has degree d. And so now H looks like, so you have a copy of H, and you have a bunch of edges protruding out. And every edge that's protruding out connects to a hole that was left by deleting a ball from the Lubotsky-Phillips-Sarnak graph. Now the result is, if you take L within this new graph that we've constructed, which I'm going to call G tilde, actually the vertex expansion of H is d plus 1 over 2. And the way to see this is, let's look at the neighborhood of the vertices in L. It's going to include the vertices in R, of which there's a d minus 1 over 2 times the number of vertices in L. And then we're going to get an extra vertex for each in L, which adds a 1 to the vertex expansion. So the d plus 1 over 2 comes from d minus 1 over 2 from H, and 1 from the extra edges that we attached. And the claim is this graph G tilde is near Ramanujan. And just to give a sense of why this graph G tilde is near Ramanujan, which I unfortunately won't have time to get into the proof, it actually is implied by the fact that if you take the graph H and you also consider all the extra edges that we attach to make it deregular, and now imagine extending this graph so that by attaching an infinite tree to every loose vertex, you get some infinite graph T, which has a copy of H embedded within. And the main thing that we can prove about this graph T is that its spectral radius is at most 2 square root d minus 1. So T is actually an honest to good infinite Ramanujan graph. And the claim that G tilde is near Ramanujan is implied by the fact that the spectral radius of AT is bounded by 2 square root d minus 1. And the two main technical components in our proof are, in first, bounding the special radius of AT by 2 squared d minus 1, and also showing that the claim that G tilde is near Ramanujan is implied by the special radius bound on AT. And with that, I'm going to end the talk. Thank you all for watching.